This is video 6 in the AC theory unit, and we're going to look at series circuit calculations. First thing we're going to look at is impedance. Now, impedance is the overall opposition to current flow in an AC circuit. So we have the opposition from XL that we looked at, inductive reactance, in the previous videos, and capacitive reactance, XC, as well as resistance. So it's going to be a combination of these things that's going to oppose the current. Impedance has got the symbol Z measured in ohms, and it can be calculated by Z is equal to the square root of R squared plus X squared. So Z is the hypotenuse of a triangle formed by the resistance and the reactance that will be at 90 degrees to each other. So basically, Ohm's law in AC is V over Z. In DC circuits, when we was just looking at resistance, the current was V over R. In AC circuits, we look at impedance, so it's V over Z. So let's look at a series circuit. This is an RL circuit. We've got resistance and we've got inductance L. So we've got resistance of 60, inductor of 80 ohms, 230 volts, 50 hertz. And we're going to find the impedance of the circuit to begin with. So there's our triangle again, and we're going to use Pythagoras to find the impedance. We've got the resistance and XL, so we square both, add them together, take the square root, and we get Z to be 100 ohms. The current drawn from the supply is V over Z. So it's going to be the 230 volt supply divided by that impedance that we just found, 100, and that will give us 2.3 amps flowing in the circuit. The power factor of the circuit is going to be the resistance divided by the impedance. So it's 60 over 100, and that gives us a power factor of 0.6. Now we can use that power factor to find the phase angle, and the phase angle is the angle between the resistance and the impedance of that triangle. Now the phase angle is going to be the inverse cosine of that 0.6 that we just found, and that gives us 53.13 degrees. We're going to get a volt drop across the resistor and the inductor. So across the resistor is back to our Ohm's law, I times R. The current is 2.3, the resistor is 60, gives us 138 volts. Across the inductor, similar to what we just did for the resistor, but we're going to times it by the reactance of the inductor by 80, and it gives us 184 volts. Now if we add those two voltages up, we're going to get over 300 volts there. So Kirchhoff says that the two voltages added together should be 230 volts. And if we add them, if we just simply add them, we're going to get over 300, so that we can't just add a resistive voltage and an inductive voltage. We need to use a phasor diagram. So here's our reference of current, because in a series circuit, current is constant, and so that's our reference. Our resistive voltage is in phase with the current, but our inductive voltage is leading the current by 90 degrees. Remember, the current in an inductive circuit lags behind. It takes time to reach its maximum. The resultant of those two voltages can be found using parallelogram. So we can put this line here that's parallel to the 184, and this line that's parallel to the 138, and then the resultant will be the hypotenuse of that triangle, and that will be Vs. And if we measure that by drawing these lines to scale graphically, it comes out to 230 volts. So Kirchhoff is correct that this resistive voltage plus the inductive voltage does equal the supply voltage, but it's only if we add them by phasors. And we can do it by calculation. VR squared plus VL squared, all square rooted, will give us 230 volts. We can check the angle using a protractor, and then we can see that the angle was just over 53 degrees. The resistance and the capacitance in series, so similar to the inductor and resistor. Now this is an RC circuit, so the same procedure. We're going to find the impedance, which is the hypotenuse of that triangle. And instead of using XL, we're going to use XC. Square them both, take the square root, find the impedance, 76.16. The current is going to be V over Z. 230 divided by 76.16 gives us just over 3 amps. The power factor, R over Z, gives me 0.394. The phase angle is the inverse cosine of that number, which gives me 66.81. The voltage across the resistor is going to be I times R, is that 3.02 amps times my 30 ohms of the resistor, gives me 90.6 volts. And across the capacitor, I times XC, is that 3.02 times 70, gives me 211.4. And again, if we just added those, over 300 volts. But we know we need to add them by phasor. Now I'm going to draw my reference up there because my VC, my voltage across the capacitor, is going to lag the current. So that's going to be drawn down, and I've used a ratio there. 1 centimeter is 20 volts, and that length is 10.55 centimeters to give me 211.4 volts. My phasor for my resistor is 90.6 in phase with the current. Remember, the voltage across the resistor is always in phase with the current. And I can draw my parallelogram, find the resultant, use the scale to get back to 230 volts. We can find that by calculation again. We can square both the resistance voltage and the capacitive voltage, take the square root, and we get back to 230 volts. And I can use my protractor to check my angle, and we can see it's about 66 degrees, which is what we calculated before. Now if I've got all three components in there, an RLC circuit, I've got an inductor, a resistor and a capacitor, then the capacitor and the inductor are going to be working in opposition. So the overall reactance, the resultant reactance, is the difference between the two. So we've got 80 for the inductor and 50 for the capacitor, and so the difference is 30. And it's that resultant reactance that we're going to use to calculate the impedance of the circuit. So if we go back to the triangle, the X value there is that difference value. So the impedance is going to be the resistance squared, which is our 40 squared, plus 30, which was the difference, gives us the square root of 2500, gives us 50 ohms impedance. The current is going to be V over Z, 230 divided by 50, gives me 4.6 amps. Power factor, R over Z, gives me 0.8. And if I find the inverse cosine of that 0.8, gives me 36.87 degrees. Volt drop across the resistor, I times R, gives me 184. The volt drop across the inductor, I times XL, gives me 368. And the volt drop across the capacitor, I times XC, gives me 230 volts. So we've got quite a lot of voltage there. If we added all those three, we'd get over 700 volts. But we know that we have to add them by phasor. So I'm going to choose a scale of 1 centimeter to equal 40 volts, and that will give me the lengths of the three phasors that I have to draw. Let's put that down there. Let's put our reference in the middle. Our resistive voltage goes in phase with the current, so 184. Our inductive voltage goes leading the current, So 368 volts up, and our capacitive voltage goes down by 90 degrees, 230 volts. Now, like the overall reactance was the difference between the two XL and XC, the overall voltage between the VL and VC is the difference between these two. And so we can see VL is bigger, so we can take away VC, the value of 230 volts. And that will give us this voltage here in red, which is 138 volts, which is the difference between VL and VC. I'm going to take away those. There's our resultant inductive voltage. And to find the supply voltage, the resultant, we find the parallelogram with the resistive voltage, find the resultant, and we find that that goes back to 230 volts, or close to 229.24. There's our overall phasor, so there's the difference between the two, and the phasor of 230 volts, that we can check the angle, and we should see close to 36 degrees, which we do. Our angle there from the reference to the red phasor there is about 36 degrees. We can check that by Pythagoras, but remember we need to find the difference between the two voltages before we square them. So it's 184 squared, which is the resistive voltage, plus 138 squared. Now that 138 is the difference between VL and VC. And that calculation goes back to 230 volts.